There is a question that has been bugging us for a long, long time. Do pirates reduce global warming? We are scientists. We look at evidence-based facts. Here we have the number of pirates worldwide, and we have the average global temperature. And you see, as the average global temperature decreases, the number of pirates increase. So, in other words, a lack of pirates causes global warming. But we have taken this regression course, right? So we are smarter than that. And we know that when you have points on a graph, they just sort of look like there's a line, but we know they have to be significant. So what we do is we regress one variable on the. If we do that, there are only 7 observations here, right? And so how significant could that be? Oh, it's significant indeed. 0.002. 0.002. Well, that's clearly less than 1% even. So we have a significant effect. It's very inconvenient because now we have to think, right? We can't just say one causes the other because we think, well, maybe we heard that regression is about association and not causal. Well, the number of pirates decreased over time, and the average global temperature has increased over time. Might those two variables maybe be correlated? Let's look at that. Here we have a plot of the number of pirates worldwide as a function of the year. And we see also that the number of pirates generally decreased in the modern age. Around 1870, I guess there was a spike. And then now we have very few. Okay, so when we now look at the year and the average global temperature, there's an increase. So that also looks correlated, right? So everything is correlated. But we have heard of multiple linear regression. So we can put both variables into the regression. So we have both the time effect over year and the pirates. And now we find that based on this regression, the number of pirates is irrelevant. It's not significant. Based on this regression, the association is with time. So over time, we have experienced larger average temperatures, or adjusted for a time trend, the number of pirates is no longer significant. That's a relief. Now, association is not causation. There's a tendency, though, to interpret the regression output as causal simply as a matter of just using language. That's not correct. It is an association. On average, so here's a statement that is good. On average, each additional bedroom increases the house price by $20,000, given all the other variables in the model. That's perfectly reasonable because, you know, who has the time to worry about all these details? A better statement would be, on average, each additional bedroom is associated with an increase in the house price by $20,000, given everything else. A statement that would be incorrect would be, on average, each additional bedroom causes an increase in the house price by $20,000, because we're doing regression, and regression is about association. So when I said this was perfectly fine, what I meant is simply that the language is getting more complicated and the sentence is already complicated enough. Now, how do we get causal statements? Well, the best way is through randomized experiments. And the randomization ensures that the distribution of both known and unknown confounders those are X variables that are not in the regression model or may not be in the regression model, is approximately the same in all the experimental groups. So if you randomly assign half of the patients to a new drug and half of the patients to the placebo, then you're going to have old patients in both groups, and you're going to have roughly the same fraction of old patients in this group. And you're going to have men and women in both groups and roughly the same fractions. And if there are vulnerable groups on which this drug works especially well, you're going to have roughly the same fraction of these vulnerable groups in the two experimental groups too. An introduction to experimental design, which is a separate topic, is taught in Statistics 372. Of course, what you do in the end, once you've done the experimental design, you still end up running a regression or the equivalent of a regression. And when you have the randomization, then you can make this causative statement. And the advantage of the randomization is you may not even need to adjust for additional X variables, right? Because you already know everything that is included. So, having said that, what would we do if we wanted to experiment with pirates? One possible experiment that you might design is we're allowing for 3 experimental groups: no pirates, 30,000 pirates, and 50,000 pirates. Then randomly we assign one of the experimental groups to each of the next 30 years. So that, for example, next year we have 30,000 pirates, the year after we have no pirates, and then we have 50,000 pirates. Every year a new number of pirates. So each year we recruit and train the corresponding number of pirates, and they get 1 year to be pirates. And because this is scientific experiments, the pirates can't just be called pirates. They must actually do what pirates do, right? I'm not going to spell this out here, but they have to be pretty persuasive in their piratry. And then after 30 years, you have 30 observations. You have randomized them, so the time trend goes away. And we regress the observed global temperature on the number of pirates. There's one flaw: it's not ethical. And that is the problem why we cannot always run an experiment, and why regression and adjusting for regression lives on. This is the end of the regression course. We will continue in the next segment with control charts.